Again, welcome to College Algebra. In these lectures, we're going to discuss about operations on functions, and that will be arithmetic operations on functions. So we're going to learn how to add, subtract, multiply, and also divide functions in a specified domains. Also, we're going to write functions as a sum, differences, products, or quotients of other functions. So we start with how to add and subtract, multiply, and divide functions by specifying domains. So here we say that adding, subtracting, and multiply and dividing functions. So if we have the ranges of a function f and g are a subset of the real numbers, then the sum of f and g denoted at f plus g is defined as adding f plus g at x, which is the same as f at x plus g at x. So here we say if we have two functions, let's say we have a function f at x and g at x. To add the functions, we just add them together. Also, the same thing applies to the difference. If I have two functions, f at s and g at s, and I want to find the difference, again, I'll combine the two functions together. And with products, also the same. I have two functions, f at s and g at x. The product, again, I will multiply the two functions together. With the quotient, I have a function f at s and g at s, and I can find the quotient of f at s by g at x. Here we have to make sure the denominator is not equal to 0. Otherwise, the answer will be undefined. So here we say the denominator should not be 0. So the domain of each function, unless otherwise restricted, is the set of real numbers x that are in the domains of both f and g. In the case of quotient f by g, there's a restriction that the denominator g at x should not be 0. So let's start with an example. Let's say we have a function f at x equal to x squared minus 4 and g at x equal to square root of x. Now, to find the sum of f and g, it means we are going to add f at x plus g at x. The product means we're going to multiply the two functions. Quotient means we are going to divide f at x by g at x. And also we have another quotient, we divide g at x by f at x. So first, we find the domain of f and g. Now, when I look at this function, it's a polynomial. We don't have no square root, and also we don't have no denominator. So the domain of f at x will be any value or any real numbers from negative infinity to positive infinity. Now, with the second function g at s, we have a square root. And we know a square root of a negative value, we cannot find the answer, it's undefined. So the domain of this function will be any value that starts from 0. It have to be a positive. So any value that is greater than 0. A negative value is impossible here. So that's what we specify here. We say because square root of x is to be a real number, the domain of g is the interval from 0 to positive infinity. It cannot be a negative value. So let's start with the addition A. F at s plus g at s means f at s is s squared minus 4 plus g at s is square root of x. So we combine these two terms. So the domain of f plus g consists of the numbers x that are in the domain of both functions. So this will be, again, f at s will be from negative infinity to positive infinity. But g at s is square root of x, and it have to be only positive value. So from 0 to positive infinity. So this means we have 0 to positive infinity we are going to use. So the domain of f plus g is from 0 to positive infinity, because 0 and positive infinity is a domain that is common for both f at s and g at s. So that will be the domain for both. So again, our answer will be, again, here we cannot combine, there's no like term. So the answer will be x squared minus 4 plus square root of x. Now let's do the product. F at x times g at x. So I'm going to multiply the two. So x squared minus 4 times square root of x, which will give me x squared square root of x minus 4 square root of x. So the domain of f product g consists of the numbers x that are in the domain of both f and g, and again to be 0 and positive infinity again. Then C, we looking for the quotient of f by g. So f at x divided by g at x. Since g at x is not equal to 0, then our answer will be x squared minus 4 divided by square root of x. X squared minus 4 again is f at x. Square root of x is g at x. Then we have g at x divided by f at x. So our answer will be square root of x divided by x squared minus 4. Here we have to be careful. We are doing quotient, so the denominator can never be 0. So if s is 2, what will happen? We are going to get 2 squared, which will be 4. 4 minus 4 is equal to 0. So here we have to make sure that s is not equal. The domain will be s is not equal to 2. So that's why we have the domain again. We are starting from 0. We end before 2. Then after 2 to positive infinity. Not exactly 2. We can write this also in the form of s not equal to 2 for the domain. And also we have square root of x here, so we cannot use a negative value at the denominator. And the numerator cannot be a negative value. So that's why the domain starts from 0 to positive infinity. A section of 2, we have to take 2 out. So this means we can't have a square root of negative value, and we cannot divide a value by 0. So which means x shouldn't be a negative value, and at the denominator, x also shouldn't be 2. So next we move to write function. We are going to write function as a sum, differences, product, or quotient of other functions. So here we have a function h at x, which is x squared plus 3s plus 2. And they said we should find two functions, f and g, such that f plus g equal to h, and also f times g equal to h. Here there are so many possibilities. Example 1 can be f at s equal to s squared, then g at s will be 3s plus 2, which will give us the sum of the two, will give us s squared plus 3s plus 2. Because here we say f plus g is equal to h. H is given. Another option can be f can be s squared plus 3x, and g can be 2. So here we write f plus g at x is f at s plus g at x. So this will give us s squared plus 3s plus 2, and we get the answer s squared plus 3s plus 2, which is h at x. Another possibility, as we said, we can use s squared plus 3s to be f, then g to be 2. Or we can use 3s plus 2 to be f, and g will be s squared. Yeah, we get the same answer. Again, this question said we should write two functions, f and g, such that f plus g will give us h. Now the next will be f times g will give us h. We know h is s squared plus 3s plus 2. And the best way to do this is to find the factorial so that we get product of two terms. So we know a factorial of a trinomial here, we have x squared, so we have x and x. Then we look for two values. When we multiply, we get 2. When we combine, we get 3, and it will be 2 and 1. 2 times 1 is 2, 2 plus 1 is 3. So we get s plus 1 and s plus 2. So in this case, we can say f at x is s plus 1, then g at x is s plus 2. So when we multiply, we get the same h at x, which is s squared plus 3s plus 2. So that will be the conclusion for these lectures. Again, in these lectures, we learn how to perform arithmetic operations on functions. Example, adding, subtracting, multiplying, dividing. So if we have, in general, the terminology will be with addition and subtraction. When we have a function, we combine the like terms. So if it's addition, add them together. If it's subtraction, we divide them. Multiplication and division, we multiply straight. And it doesn't have to be the same like term. We multiply using the laws of exponent. With division, also the same concept. And here, a function will be given, and we have to break it into two, either as the sum, the difference, product, or quotient. When it comes to products and quotient, we have to use factorization. But sum and difference is very straight. We can break the function into two, one part sum, the one part, two parts, and we can sum them or find the difference of the two. So that will be the conclusion of our lectures here. So again, wish everybody the best and thank you.